Hello everyone, welcome to Continuum Mechanics. In today's lecture we're going to evaluate and learn the different rules concerning vector cross products. So for two vectors, a vector u and a vector v, there exist 9 possible products of their components. Previously we looked at the scalar dot product, and we found that dot product is the sum of 3 of those possible products of components. So if we look at it, if we do the dot product of u and v, we'll find that it's a sum of 3 components, u1 and v1 plus u2 and v2 plus u3 and v3, right? Now our remaining 6 of the 9 terms can be combined in pairs to form a vector. And when we do that, we are performing the cross product, where the cross product of a vector u and vector v can be described in component notation as the u components, the EI base vectors, cross the v components with base vectors j. Now if we rearrange and commute out the scalar quantities, the scalars meaning ui and vj, we end up with the operation of the cross products of the base vectors, EI and EJ, right? So our scalars come out, and in essence it's the cross product of the base vectors. Now let's consider the cross product of base vectors. Let's actually perform that operation so we get a better understanding of where the product of the cross product comes from. So let's consider the base vectors 1, 2, and 3. And let's perform the cross product of base vector 1 cross base vector 2. The result of that, which we know from earlier lectures, would be our third vector, our third base vector. And we can graphically show that as vector 1, vector 2, where our third vector is the normal of the surface that is formed by E1 and E2. And note that we are crossing 1 with 2 to get our third normal vector from the surface, right? And this is all according to our right hand rule, right? So where our fingers, the first vector E1 is our first finger here. The second vector is the second finger, and the thumb represents the direction of the cross product. Now if we were to switch the order here, so say we were to switch the order and say that we want to do the cross product of base vector 2 with respect to 1, well, we'll find that our solution is actually negative base vector 3. In essence, what we've done is we've switched the order in which we perform this operation, and in order to maintain the right hand rule, the sense of the normal must be negative. And so in essence, based on using the right hand rule, we find that the cross product is actually anti-commutative. So we can find the following relationships between these our three base vectors. The cross product of base vector 1 and base vector 3, base vector 2 is equal to the negative the cross product of base vector 2 and base vector 1. The cross product of base vector 2 and base vector 3 is equal to the negative the cross product of base vector 3 base vector 2. And then finally, the cross product of base vector 3 and base vector 1 is equal to the negative of base vector 1 cross product base vector 3. So we've got this nice little beautiful relationship that tells us if we're going in the order 1, 2, 3, our opposite sense or the other side, the anticommutative nature, would be in the opposite direction. Be going 3, 2, 1. So for instance, the left-hand side, 1 and 2 is here. The right-hand side is going from 2 to 1, right? So we can see that the order of the terms can help us to actually derive each of these anticommutative relationships. Now another thing that we find, another set of expressions we find, is that the cross product of base vector 1 with itself, cross product of 2 with itself, and the cross product of 3 with itself are all equal to 0. And why are they equal to 0? Well, the cross product is basically forming a surface that we can find a vector that's normal to that surface. But when we have two vectors that are the same, we're not creating a surface, and thus there is no vector that's formed because there's no surface, right? Okay. So these equations, these 6 equations, the ones that tell us the cross product of I and J when they're not equal, and then also the ones that tell us the cross products of KK, meaning when they're equal, can be expressed in a simplified form, in a compressed form. Cross product of I with respect to J, so cross product of base vector I and base vectors I and base vectors J is going to be equal to this epsilon ijk base vector k, where our symbol epsilon ijk is our permutation symbol, and it symbolizes the following operation, where epsilon ijk is equal to one of 3 options. It's 0 if I is equal to j. It's positive 1 if the order of our operation is from I to j to k. And it is negative 1 if the order of our operation is from k to j to I. So let's note, this is a representation. For instance, the ones that are plus 1 is a representation of 1, 2, 3, increasing order, right? While the negative 1 correlates to a decreasing order, 3, 2, 1. And there are multiple permutations of this order. So let's look here. For plus 1, there's 1, 2, 3. There's 2, 3, 1, and there's 3, 1, 2. Right? Different combinations of those numbers in sequence. Negative 1, there's 3, 2, 1. There's 2, 1, 3. And there's 1, 3, 2. Right? So these different permutations will tell us whether we have a positive or a negative or zeros. So with this knowledge of the permutation symbol, which can tell us what happens with our cross product based on the indices, we can redefine the solution of our cross product with a vector W and component notations. So the components U, the components V, which is the cross product of base vectors I and base vectors J. Well, we can simply rewrite this as UI Vj eta I j k base vectors k, where that k is a dummy indice. Now, when we work these indices out, when we actually perform these operations to determine the terms of this cross product vector W, we'll find that W is going to be equal to the following: so U2 V3 minus V2 U1 base vector 1 plus U3 V1 minus U1 V3 base vector 2 plus U1 V2 minus V1 U2, our third base vector. So we've actually, if we go ahead and exercise these indices, we can find the form of this cross product vector. And what is great about this form is that it's actually equivalent to performing the determinant of this set of vectors, where the cross product is equal to the determinant, where first row are our base vectors, second row is U1, U2, U3, and our third row is V1, V2, and V3. Now let's remind ourselves about dot products. We cross out the first row and column, we multiply by that first term, and then we cross multiply minus this term to produce the first element. And we repeat that process in order to get our additional two elements, shifting our placement of what's shifting the row and column that's crossed out. So here and here would be the second term, and our last term would be this one and that one, and we'd be able to build up the initial form that we found here, this fully worked out form, which is great, right? So now that we've kind of introduced this permutation tensor, we've actually worked out what is the cross product of two vectors and found that, hey, it's actually the determinant. Let's go ahead and look at some of the properties that we can get from the cross product. And let's start with verifying our findings about the cross product in index notation. So let's say we're doing the cross product of U and V. We remind ourselves that that is equal to UI. Let's move this up a little bit here. That is equal to UI Vj epsilon ijk base vector k. If we introduce, if we introduce a minus sign into our permutation tensor, then we can say that our epsilon ijk is equal to negative epsilon jik, right? So we're simply, if we change the indice order, we change the sense and we add a negative to make it equal. Now if we were to do that, so if we did that, noting that we've changed the order here of our indices, then we're going to be forced to reorder the position of our components in the way that we multiply our components here for the components UI and Vj. So we'll end up with Vj ui negative ijk a to k, if we wanted to have consistent indices. So with this negative sign and the change in the order of our v and u, we'll find that u cross v is actually equal to negative v cross u. So simply using our indices here in the permutation, we can find that anti-commutative relationship that exists when we're doing the cross product. Now, one thing we need to remember is that the cross product is orthogonal to the vectors of the in the product, meaning that if we have a product, so u cross v, we are forming a surface of u and a surface of v. Well, not a surface, we're forming a vector u, a vector v, which create a surface. And our product, w, is orthogonal, meaning normal to that surface, right? So that indicates to us that there's 90 degrees between each of the terms, or each of the vectors in this cross product. So if the cross product exists, then when we distribute that knowledge, or when we then try to perform the scalar dot product of these vectors, we should find that the scalar dot product is equal to 0. And this all arises from, if we remember that if we have some vector A and some vector B, that the dot product A dot B is simply the magnitude of A and B times cosine of theta, where theta is the angle in between those vectors. So if the angle is 90 degrees, meaning if it's orthogonal, if the vectors are orthogonal, then A dot B is equal to 0, right? So we're just reminding ourselves of that relationship. Well, then what happens so we know that relationship? What happens if we then perform the dot product of u with respect to u cross v, where we know that u cross v is w, right? Saying these are orthogonal vectors here. Well, let's use our index notation and let's see if we can prove that this equation should equal to 0, meaning u dot w is equal to 0. Well, let's go ahead and break it down to the components. So we know the u vector is the ui components times the vectors with I, and we're doing a dot product here. And let's introduce our permutation tensor here, and let's actually reorder this. So let's lead with our permutation tensor, giving it indices k, l, and m, where u is k, v has indices l, and our base vector has the indices m. All right, so now that we have that, let's commute out our scalars. So ui, uk, and vl, those are scalars. Let's commute those out. ui, uk, vl, and then let's perform the dot product of our base vectors. So the dot product of base vector with indices I and base vectors indices m. And let's have our permutation tensor on the outside here, epsilon k KLM. Now, if we remember from previous lectures, when we do the dot product of base vectors, we can actually find our Kronecker delta, right? So when we do that, this regresses further to UI, UK, VL, the Kronecker delta, IM, and epsilon KLM. And let's note that that last indice on both the Kronecker delta and the permutation is M, so we can actually contract this further, knowing our permutation is simply a bunch of zeros and ones, depending on their position. We can find U, I, UK, VL, permutation, KLI. Now, when we exercise this series of indices, we're actually going to end up and find, when exercising these indices, considering the permutation, that our final solution here is equal to 0. And so, through using our indices and our permutation tensor, and actually filling in each of the terms, we'll find the product here is equal to 0, proving that given orthogonal vectors, given these relationships, that the product here, the scalar product of these vectors, is equal to 0. So another property that we're interested in exploring is the triple scalar product. And scalar tells us that the product here is going to be a scalar quantity. Now, we introduced this earlier. We introduced this when we went over vectors earlier. And the triple scalar product is gives the volume of the parallel pipe with vectors u, v, and w as the edges in the following form, where the triple scalar product is simply u cross v dot w, and noting here that we are considering these vectors as non-coplanar. So these are not orthogonal vectors to each other. They do not carry that 90 degrees angle with respect to each other. So we can try to draw these if we would like. So let's draw these. Let's draw first a coordinate system that is orthogonal, and then let's draw our vectors that are not orthogonal to each other. And we can say that the volume formed by these is our triple scalar product here. And let's actually fix this a little bit. This is not the perfect little drawing. I'm not an artist. Wish I was. Could make some really beautiful little images here. All right. And we're saying that we are not orthogonal. Something like this. Something like that, yes. So, so then how do we actually find this triple scalar product? Well, let's go ahead and try to break it down into component form. And let's use the permutation symbol to help us to do that. So u cross v dot w, let's define that as the permutation. So let's lead with the permutation, eta jk ui vj and wk. And note here that this is a scalar, right? We're finding a scalar quantity, and we're using the dummy variables to indicate that we're summing these terms with additive terms together, right? Now, if we were to exercise this, so actually exercise these dummy variables and plug in our terms, we can find an expression for this triple scalar product as a determinant. where u cross v dot w is going to be equal to the determinant u1, u2, u3, v1, v2, v3, in terms of w1, w2, and w3. And again, the same procedure for finding the determinant. For the first term, we cross out the first row and the first column. We multiply by that very first element, and then we cross multiply, subtract, cross multiply, and we repeat that process, putting a negative sign in front of the second term to perform the determinant. And so we can actually, and we'll, later on, I think in the next lecture, we'll actually go into more detail on the determinants, so you can actually see this process, and we'll work through some examples, right? But a cool thing that we'll find is that our triple scalar product will vanish. It'll actually be equal to 0 if our vectors u, v, and w are coplanar. So meaning if they are orthogonal to each other, 90 degrees with respect to each other, they'll vanish, right? And that is pretty much the previous example that we had, but with a different order of the operation in terms of dot products and cross product. Okay. Now let's do another operation. Let's look at another operation we can perform, which is the triple vector product. And this is the cross product of u with v and the cross product with w, right? Now if we complete this operation and put it into component form, then we can do the following. We'll find and let's arbitrarily set here our indices. Component uj and base vector ej. There we go. Cross the base vector k, or permutation klm, our vector, or our components of vector v with l, and and w with m, right? Where in essence we've used our permutation here once, and we're still doing the cross product of these individual elements. Now when we take these elements together, when we actually take these elements together, let's note that, hey, we pull these the cross product of these two base vectors, we're going to introduce another permutation tensor, right? So if we do that, and we note what indices, how the indices would shift, then we'll find base vectors I, a permutation tensor here ijk, our permutation tensor here k, l, and m, with uj, vl, and wm. And so when we are going to do multiple cross products, we've got to figure out how we then collapse and what indices we would indicate for our new permutation tensor. Now, a great thing that exists is an identity that exists between our permutation tensors and the Kronecker delta, which can simplify this process of performing multiple cross products. So the relationship is as follows, where permutation of I, j, k, and the permutations of I, m, n is equal to the Kronecker delta jm, Kronecker delta kn, minus Kronecker delta jm, and Kronecker delta km. Oh, and we got a little typo here. Sorry about that. It is the Kronecker delta J and Kronecker delta Km, right? Now, if we take this relationship that exists and we rotate the indices, so rotate the indices of these two so that they match, then we can actually exploit this identity of the Kronecker deltas in order to solve for our triple vector product here. And we'll find that U cross V cross W is going to be equal to VI EI UK WK minus WI EI UK VK. And this then subsequently can be put back into coordinate free form as follows, where this is V U dot W minus W U dot V. So we found another expression for that triple cross product. Now that we've explored the cross product and the different products we can form of it, let's actually look at how we would apply the cross product in real life. The example we have here is the velocity due to rigid body rotation, and this is the example from the book. So this problem is set up as follows. A rigid body. In a rigid body, the distance between any 2 points is fixed. Consider rotation of a rigid body with an angular velocity omega about an axis designated by the unit vector n. And we say that our angular velocity vector omega is equal to the angular velocity about this axis. So we can basically define that, hey, there's some normal. There's this angular velocity omega that's happening about it. And we want to define what is the velocity of a particle or a rigid body within this system. So say there's some particle that's at a distance and it's rotating about this axis n. What is the velocity of that particle? So how would we use the cross product to find that velocity? Well, we can look at it schematically. So we can go ahead and try to draw the vectors in a coordinate system and try to define, okay, what is the velocity of this particle? So let's do that. So let's start with the same points we had previously. So say O is our origin. Point O is our origin, and point P is our particle, and the distance from the origin to the particle, let's say that is a vector x, or let's just say this is a vector from O to P, right? And between the vector x and this direction vector n, there exists an angle. theta. So say theta is the angle between the position vector for P and the normal about which we are rotating, right? Now the vector, the cross product of our axes n and the position vector x is in the direction P prime and has a magnitude. Now what is P prime? P prime is a position of the particle P after a period of time, after we've moved through time, right? After this velocity has had time to act. So we're at point P, the angular velocity acts, we move towards this new position P. And if we were to define a triangle about where these points, point P and point P1, meet on our axes, well, we can define a point Q, which has a distance relative to our origin. So we can actually define this distance from our origin along the axes of rotation, right? So the vector that is the cross product of n and x is going to be in the direction is going to be directed from P to P prime. And it'll have the following magnitude. Because n is a unit direction vector, so its magnitude is equal to 1, it'll actually be x sine of theta. It'll be equal to a magnitude of P and Q, right? Where P is the magnitude of the x vector, and Q is the magnitude of the projection on the normal direction vector. So in essence, this is the perpendicular distance from P to the axes of rotation, right? And remember, we're using our right-hand rule. And using our right-hand rule, we know that we're going to be going back into the page, right? So from this, if we then consider time, so we consider that the change in position from P to P prime is happening over some increment of time, then we can define what the displacement is of this particle in space. For the displacement vector is going to be equal to the angular velocity about that axis of rotation, and the cross product of that with respect to the position and time, right? Now if we took the limit of this and we approached 0, so we approached a 0 time increment, then we can actually find the velocity of our particle, which would be the angular velocity cross our position vector x, right? So in essence, we're finding that we're creating a surface of x and n, and that surface is telling us the direction. It's orthogonal to those. It's telling us the direction that our velocity is going to take, right? And by integrating time into this equation, we're actually able to find the velocity of this particle. And so this is an example of some of the things that we can do with the cross product. There are other examples in the book. I think there's an example for momentum with a system of particles, which is a good example to review from the book. And then there are some other examples in the book as well. So that's pretty much covers section 4 of the book. In our next section, I believe we'll be looking at the determinants. So we'll actually take some time to actually perform that determinant operation and illustrate to you step by step how to properly do it. And then we'll continue doing these mathematical preliminaries. So that's it for today's lecture. Look forward to seeing you in the next class.